Hey, how's it going everyone, and welcome to my PyCon 2020 tutorial on natural language processing in Python. I'm bummed that I couldn't be there in person to share this with all of you, but this online presentation is the next best thing, so I'm excited to get started. Before we actually jump into the contents of this tutorial, I thought it'd be useful to kind of set the stage. The past 2 years have been really exciting for natural language processing. I would say starting in probably with late 2018, a lot of really influential work was being published. It seemed like each new paper was kind of more influential than the last, and performance benchmarks were being broken left and right. And I think the period can be pretty well captured with this news headline I remember stumbling upon in 2019, and that is, "New AI fake text generator may be too dangerous to release," says creators. This happened at the time when OpenAI had built this OpenAI GPT-2 language model, and they were scared that people were going to generate all sorts of fake news stories and maliciously use their model, that they hadn't initially released the full set of parameters. They ultimately did release these parameters, but I think that this kind of headline captures an important changing point in natural language processing, and that was that for the first time we had been building these models that captured the language semantics that we never had previously been able to before. And for the first time, we were really doing things that were crazy and scary and powerful at the same time and really impressive. And so for this reason, I'm really excited to share this tutorial with all of you. It's an exciting time, and in this tutorial, we'll kind of walk through, we'll start with the basics and kind of some of the more traditional NLP models, and we'll walk our way up to some miscellaneous NLP techniques, all the way up to these state-of-the-art language models like OpenAI GPT-2. So this tutorial is going to start with the basics. It's going to start with kind of the NLP fundamentals. We're going to look at basically how you can take text and convert it into a numerical vector. And probably the easiest way to do that is what's called bag of words. So that'll be the first model we look at. We'll spend a little bit of time, high-level overview of it, and then we'll jump into Python code related to it. Then the next thing we'll look at is a slightly different variation of how we can convert text to a numerical vector, and that will be a word vector approach. And we'll also see how we can use Python code to implement models that use word vectors. After we go through kind of the NLP fundamentals, we're going to go through all sorts of different miscellaneous NLP techniques. So we'll go through regexes, basically pattern matching in Python. We'll go through stemming and lemmatization. We'll go through some basic spell correction, some basic part of speech tagging, and we'll finish this tutorial off by kind of giving it a high-level introduction to the state-of-the-art models that I mentioned. So this OpenAI GPT-2 model, and more generally, transformer, what is called in transformer architectures. So another big name one is BERT. So we'll kind of introduce and see how those came about, and I'll show you how you can use Python code to play around with those and build even more powerful models. A little bit about me. My name is Keith Galli, and I currently work at a company called Posh Technologies. We're a small software startup that builds chatbots and other conversational AI solutions for a wide range of enterprise customers. At Posh, I worked a while on our intent recognition models for chatbots. So actually how the chatbots take in text and process that automatically to kind of understand what a customer is asking it. In addition to that, one of my hobbies has always been teaching, and ultimately that's kind of what leads me to give this presentation today. But also I, on the side, run a YouTube channel, youtube.com/kgamit, where I post all sorts of Python content and specifically a lot of data science tutorials. And then the last thing I wanted to say is that I'm bummed that PyCon is not in person this year. I would love to connect with everyone, so feel free to reach out to me on LinkedIn, Instagram, Twitter. If you search up Keith Galli, one word, you'll probably find me. The first model we're going to talk about is called the bag of words model, or also sometimes called bags of words model. And to give you a little bit of intuition behind this approach, I mean, whenever we're doing any sort of data science related task, we like working with numerical vectors. And obviously our issue with text is it's not a numerical vector. So this bag of words approach is kind of the easiest way to take sentences and pieces of text and convert it into a numerical representation. So imagine we have the four utterances: I love the book, this is a great book, the fit is great, and I love the shoes. These come from two different types of categories at our retail store, the books department and maybe the clothing department, and we're trying to build a model to tell them apart. Well, what we can do with the bag of words approach is it basically says, take all of the words that we see in all of our utterances and just extract out each individual word, each unique word. So that would give us, I love the book, this is a great fit, and shoes. Take all of those words, and then based on what words, which of these sentences have which of these total unique words, we create a vector where a 1 represents this sentence has the word, and a 0 represents it doesn't. And so that's the basic approach of a binary bag of words model. And so what does that look like in code? Well, I think whenever we're building a bag of words model, the easiest library to use is the scikit-learn library. So we're going to extract a couple things from the scikit-learn library. I'll make my text a little bit bigger. From sklearn.feature extraction.text import count vectorizer and we'll just start with a count vectorizer. So when it says count vectorizer, this can be either a binary bag of words that we just mentioned, 1s and 0s. It also could be, if you imagine one of these phrases I mentioned, I love the book was great. If that was all like one sentence, maybe a count vectorizer could also say that book appeared twice. So it would be a straight count of the word in the overall sentence, how many times the word appeared in a sentence. But I usually just tend to use a binary approach. If you ever don't know how to find something like this, if you know of the bag of words model but you don't know where to look to find it, I just literally would do like a Google search sklearn bag of words, and you'll get to the scikit-learn documentation, and through that you should be able to find some examples using bag of words basically. So like here we have the count vectorizer that I just showed you, and it shows us how to utilize it. So we might reference this a couple times as we do this. So we have our count vectorizer, and above this I'm going to just real quick define some training utterances. So I'm going to call this train X. I'm going to say, let's use our examples. I love the book is the first one. I love the book. This is a great book was the second one. And then the last two were the fit is great and I love the shoes. All right, so that's our 4 training utterances we can imagine. So the first thing we might want to do is utilize our count vectorizer to transform this into a vector representation. So once again, I'm going to reference the documentation here. And I know what I'm trying to do, but I sometimes forget the syntax, so this is why I always reference documentation like this. So it looks like we want to use vectorizer.fit transform. So vectorizer equals count vectorizer, and then fit transform on our sentences. So we can do that. So we can say vectorizer equals count vectorizer, and then we can say our vectors are equal to vectorizer dot fit transform train X. And when this says fit transform, it fits a dictionary around our training utterances. So basically that's the first step, and it's finding all the unique words so it knows how to make these vectors, and then it's going ahead and transforming the utterances we pass in based on that vector that we just fitted. So now we get our vectors. So I could do like print vectors 0, and it'll be the vector for I love the book, if this runs. Train X is not defined. Oh, I need to run this still too. I'm using Google Colab right now to run this. Okay, it looks good. I might just do dot vector, I think it is. Not found vectors. Let's just see how we print this out real quick. Oh, I guess we could do toArray to see how it actually looks. We could also do vectorizer.getFeatureNames. That looks helpful too. So I'm going to print some things out. I'm going to print out vectorizer.getFeatureNames, and I'm also going to print out, let's say, vectors, print vectors.toArray. Let's see what happens. Okay, cool. So our different words in this dictionary are book, fit, great, is, love, shoes, the, this. And one thing to note is it looks like it actually stripped away the A, so that might be just a feature of, one word utterances. It strips away part of the way that this count vectorizer is implemented. But if we look at the vector here, let's look at the first utterance. That's I love the book. So we have a 1 here for book, right? We have a 1 here for the love, right? The is the second to last, so we have a 1 there, and I guess it stripped away I as well, so we don't see that. But we get a vector representation other than the one-word utterances where this vectorizer doesn't count. And one thing to note is that I think by default, if I made this I love the book, count vectorizer is non-binary, so it actually matters how many times you type something in. So if you wanted to, you could do, I think, binary equals true here. And now it switches back to 1s and 0s. Okay, so that's the basics of the bag of words, just seeing it and making a very toy example of doing it. Let's build a quick model to actually classify these as being clothing related and these as being, these first two being book related. So I'm going to call something train Y. So that's going to be, the first one's books, second one's books. And whenever I have a repeated string like this, I like to make it its own variable, just so I make sure I don't actually like misspell it. So we're going to make a class category real quick and just label books as one of the categories, and that's going to be the string books, and clothing as the other category. And you'll see why I'm doing this in a sec. So now when I'm doing this in order, so I have 4 things. I'm going to give them their 4 labels in order. So we have category.books, we have category.books, and then the last 2 are about clothing, so those are category.clothing. All right, and I'm going to run that again. Run this again, I guess. And now we're going to build a simple classifier to, I'm going to just hide this print so you can see everything real quick. I'm going to build a simple classifier to classify whether these are a book category and this is clothing, and we can use it on new utterances. So how do we do that? Well, once again, the scikit-learn library is very helpful in this. And a good classic classification model for text is often a linear SVM. So that's what we're going to use. So we can do from sklearn import SVM, and then we can define our SVM by the following. I'm going to say classifier SVM equals svm.svc with a linear kernel, because I want to use a linear SVM because it's I know just with my background knowledge that this is a good classification model for text oftentimes. And then with that SVM, I'm going to do a fit on our training vectors, which is right here, these vectors, because we couldn't just pass in the text. So I'm going to call this train x vectors, and then our y labels, which is just train y. So this should fit a model to the 4 utterances we have here, and we got a error. Oh, I didn't rerun this cell. Cool. And then finally, let's do the fun part and predict new utterances with this. So I'm going to just call this text x equals vectorizer dot transform. So before we had to fit a dictionary and transform based on our training utterances. Now that we already have a vectorizer, we can just do transform instead of fit transform. And so I'm going to just say something like, how about I like the book. So based on what we have here, because we said the word book, you'd expect that this would classify as the books category. So we can do classifier clf svm.predict on our test x and see what happens. Nice, books. That's cool. Let's try like, I love the shoes. Maybe we say something like, shoes are all right. And wow, that says clothing. And obviously we only trained this with 4 utterances, so it's only going to be so powerful. But, so yeah, it's only going to be so powerful, but as we added more and more utterances to this, our dictionary would grow more and more within this vectorizer fit transform, and we'd get a more powerful model. So the more training utterances we feed into a bag of words model, oftentimes the better it does. And I guess one of the caveats to that is you might build such a big dictionary that it might get hard to process like the model. So another technique you can add in here, and definitely sklearn offers you some ability to do this, is maybe only take the top 1,000 words that occur. So that's like another option. Another thing to know about bag of words is right now we are doing a unigram approach where we're just taking each individual word by itself. But you could also do a bigram approach, it's called, which would categorize I love the book, all as their own unique utterances. So let's try to do that real quick. I'm gonna just see. Let's see what we have. N-gram range. That's probably gonna help us. So I'm gonna type in n-gram range because it probably will give me some more information about that. Equals. Oh, so I'm gonna say one and 2 to get, I think, both 1 words and 2 words. So we can print this stuff out again and see if that is the case. Yeah, so now you see we get 2 words as well, so that we just now captured bigrams as well. And one thing to note about these bigrams, one reason you might want to use 2 words in a row is, let's say we were talking about if things were positive or negative. Well, if I say something is great, that's very positive. But if I use a bigram and the word before great is not, not great, then that's a completely different sentiment. So that's one way, n-grams are important. And as words depend on their context. So, adding additional words in this sometimes helps. It could also be detrimental if you had too many words here in the n-gram range. You might have so many like random miscellaneous like 3-word phrases that only occur once in your entire set, and it might actually skew the classifier off a bit. So I'm going to just stick for now with just a single one unigram model. And here's the final thing I'll say about bag of words before we get into the next model is, here's the limitation, is if we have a word that is not in our training utterances, we're not going to know how to handle it. So if I said something like, I love the story, Well, to us, that's very similar, to book and books. But to our model, we've never seen the word story, so we might not know how to handle this. So let's see what happens when we run this. And here's the issue. Yeah, it classified it as clothing, even though it's obvious to us that story and book are very related. And honestly, I think even if we typed in something like books, it doesn't know that book and books are the same because it has seen the word book right here, but it's never seen books. So it's like pretty dumb if it hasn't seen a word. And yeah, again, it says clothing, even though it's very obvious to us that book and books are the same. So that's one downfall of Bag of Words, is it's great on the stuff it's trained on, but if it hasn't seen a word, then it just fails miserably. And, that's not great. When in the human language, we can say different things in so many different ways. So this leads us to the topic of word vectors. And word vectors are another approach to turning text into a numerical vector. And the big goal with word vectors is to convert text into a numerical vector that captures some of that semantic meaning in the vector space that you're mapping this piece of text to. And what I mean by that is that imagine you have the words red, blue, and yellow. These are all three different types of colors. And what we're trying to do with word vectors is we imagine you have this big vector space. We want the similar words to be mapped in a similar spot of that vector space. So red, blue, and yellow would all be colors and should be mapped somewhere similar. And there's many different approaches to training a vector to ultimately do this. And one of the popular methods is called word2vec. And word2vec works in one of two ways usually. There's two popular, most popular, I guess, ways to train this word2vec. One's called continuous bag of words and one's called skipgram. The different details of these two approaches isn't super important, but what is important is to kind of understand at a high level how they work. So imagine we're going back to our kind of example of classifying between books and clothing related tweets. So imagine we have the three phrases. We say, best book I've read in years, we have great story and characters, and we have no development of characters during book. So these are three phrases related to books. We can tell this pretty easily by reading these, but how do we train a model to see that? And what the word2vec approaches do, the continuous bag of words and the skipgram approaches, is they look at a window of text. So oftentimes that window might be 5 tokens long. So best book I've read in. So that would be kind of our context window. And basically what we'll do is we'll selectively look at different tokens in that context window. And based on that token, we'll utilize the surrounding tokens to kind of figure out the context of each token and kind of start developing a meaning of each token. And so translating that to this example, we can start, if we read enough text, we can start to see relationships between words. So, for example, here, one relationship we might develop over time is book often appears close to read. So now we can associate book and read into a similar spot of the vector space. And this is ultimately going to be trained through some sort of neural network architecture for the most part. So given our neural network architecture where, our model is learning that book and read are close together. In this next example, great story and characters. We might start relating story and characters together. And we'll see these together. So we'll know that those are related and should be similar vector space. And then this last example, no development of characters during the book. Well, maybe we relate development in characters. That's what our model's learning. Also it's probably learning that characters and book are related, and we can kind of start building out bigger relationships. Okay, we've seen characters and book here. We know that those are probably related. Okay, we go up here, story and characters are often together. So I'm guessing that story and book are probably related as well. And this is a very toy example of what's happening with hundreds of thousands of sentences being fed into these types of models. And we're ultimately building up these word vectors out of that. So it's one thing to talk about it. Let's start jumping into some Python code to actually show you what that looks like. And I think the best spot to easily utilize word vectors in Python would probably be to use the spacey library. So whenever I'm like trying to remember how to do something like this, I'm going to be doing a Google search, finding some sort of information on how I use a spacey and use the word vectors they offer. As I can see, we're probably going to have to download some word vector model because we're not going to train this from scratch. We'll use something that's already been trained. And then we can kind of follow along like this, it looks like. Okay. Yeah, and you can look through here. Maybe you look through the actual documentation, but spacey is a good place to start. And let's start implementing this. Okay, so we're going to need to use the spacey library. Before we can use the spacey library, we're going to need to download that language, these trained vectors. So I already did that previously, so I'm going to just go ahead to the top of my Google Colab file, and this also probably should work with a Jupyter notebook or whatever you're using, or your browser. If you might need to do like a pip install here, but I'm going to insert a code cell, and I want to make this above. I'm going to just do a couple installations of things that I need here, because by default the Google Colab that I'm using won't have the spacey language model or the spacey word vector model embeddings that we need. So we're gonna have to install those. So in here I can do pip install spacey. So I think spacey is already installed, but sometimes you need the most up-to-date version, and I think this will help us do that. And we're gonna do python-m spacey download. We're gonna download the medium-sized embeddings, but as we can see in this doc that I walked through, there's also a large model, but that might take a bit long to download. But if you want to try some more powerful word vectors, maybe try that large model. Okay, so I'm going to run this. It's downloading. Okay, so we've downloaded it. And one quick note is sometimes if you're using Google Colab and you do this, you might have to restart the runtime before changes take effect. Like imagine you already imported spacey. I don't think that spacey would recognize that this model is here unless you restart that runtime. So I just did that to be doubly sure. So import spacey, that's our first step. Okay, it looks like it imported properly. And now what we want to do is load in that, we're going to call NLP, that word embeddings model that I just downloaded. So N-core web medium size. So let's see if this works. Hopefully it does. We only need to load this in once, and then it'll stay in memory. And like if you're not remembering how to do this, I always like to remind people, literally just do a Google search. Word vectors, spacey, documentation. The article I was looking at wasn't the actual docs. You could probably actually find the docs here. And that will give us, yeah, look at this. This gives us some nice examples right there. And that makes it a lot easier than trying to figure it out from memory. So let's see. I want to see a actual value. Looks like vectors of values. I think I can do dot value and get my vector. All right. Okay. So what we're going to do here is basically we need to take text. So we can, if we want to, use the same text from above. So I'm going to just rerun this cell. So now we have all of these examples that we were using previously with our bag of words model. So that's called trainx. And now I'm going to say our docs equal, basically we're going to need to convert, if I can see the initialization here. I'm going to look up one more time. Word vectors, spacey, example. I just wanted an example to see how I can do things. Spacey 101. Looks like I already had clicked this next one. No! This one right here. So let's try this. Okay, look at this. Yep, there we go. This is nice. It's showing us how we can make this a little bit bigger so you can see. This is showing us how we can get that vector. If we pass in doc NLP and do vector, then we get a vector representation. And did that? Let's see. Oh, maybe the doc container had the information here in the docs. Vector, 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 vector. I want to find it here. Okay, here we go. Yeah, real valued meaning representation defaults to an average of the token vectors. So basically, if we do NLP of our phrase and then do dot vector, it's going to take all the individual word embeddings and average them together. So that's, I think, what we ultimately want if we want to build a model around this. And also to note that these word vectors are usually hundreds of, they have, you know, a dimension 1 by like several hundred. So they're pretty big, but they kind of have to be to capture the information we need. Okay, so docs are going to be NLP of text for text in our train X that we just defined. And now each of these items in this docs list is a word vector representation of our sentences that we defined above here. So I love this book. This is a great book. The fit is great. I love the shoes. And just so we have that here, it might be helpful for me to just print out train X so we can remember that. Okay, so that's what we're ultimately converting. So now if I print out docs, you're going to see that it's, oh, I guess it keeps the, if I print out docs.vector, or oops, if I print out, let's say, the first docs vector, you're going to see that this is the word embedding representation, the average word embedding for each of the words in I love the book. So that's cool. We did that pretty easily using spacey and a couple lines of code. And now that we have this, okay, so now that we have this, let's build the same model that we built for the back of words model for the spacey model. So we can define a classifier again, and I'll define it like this. So we're going to define a classifier, and I'm going to give it a slightly different name. I'm going to just say SVM, and I'll give it WV for word vectors at the end, just so we can tell these apart. And we want it to not fit to the train X vectors anymore, but we want to fit to we'll define word vector vectors, we'll say. I'll just call them train X word vectors, just to separate it a little bit from the other word vectors. And that's going to be a.vector, x.vector for x in docs. So we're just getting all of those as a list. So now we're going to pass that into our fit. And the Y labels stay the same as above. books, books, category, clothing, clothing. All right. So let's see what happens here. We're fitting this. Run this again, run this again. SVM is not defined. Okay, I need to re-import SVM from scikit-learn. Cool. I think there was one other thing I needed to re-import. Nope, I think we're good. Okay, so we have our model, and now what happens if we try to predict some novel utterances? So to do this, we can pass in NLP of a phrase. So how about I love the book? We'll just do that again here, and then we'll have to grab the vector for that. What's going to happen here? Oh, it's trying to do too much in one spot. So instead of doing that, I'm going to say test x word vectors equals, well, I'll also define a test docs. That's going to be equal to trying to do a lot here. Sorry, I feel like this is simple, but as I do this live, it's sometimes tough. So test is going to be equal to a list of words. So let's just say I love the book. Test docs now is the NLP representation of test x or text for text in test x. And then finally, the word vectors are going to be x.vector for x in test docs. Cool. So now we can predict test x word vectors. Cool. Sorry, I was trying to simplify it too much, and as a result, no. Oops. So close. How did I keep getting double things here? Okay, I love the book. Works as expected. I mean, that was an exact take from here. So that recognizes books. But now let's try to find the power of word vectors. And let's type in something like, I love the story. And we're hoping that story and book have a similar word vector representation so that when we do this averaging, when we do this NLP text, which basically averages all of those word embeddings together and actually get the vector value of that averaged embedding, that we get a book's classification again. There we go, look at that. I love the story. It gets books as well. And now let's try testing out some things for clothing related. So I love the shoes works. So if this is properly capturing the semantics, you should be able to say something like, I love the hat. And hopefully that says clothing. Look at that, cool. I love the hats. That should also be clothing. I love the books, even though we haven't seen books exactly. It now knows that book and books are more related because it's seen those in similar context windows. And yeah, there's all sorts of cool stuff that we can do with this. You know, these earrings hurt or something. And already with just 4 training examples, because there's so much power baked into the spacey word embeddings, the word embeddings in general, even just with this medium-sized model, that we can already predict a lot of things correctly just by knowing that, you know, semantic space. And I think this, like, word vectors are so cool, and this concept is so cool that we can do so much with language like this. So this gets me really excited. I guess before I end this little section, there are some drawbacks to word vectors. They're not a cure for everything. I think one thing you'll see is that it worked out pretty well for us because we only had 2 categories. We only had books and clothing. But if we were trying to use word vectors by themselves, and I think at the exercise at the end of this tutorial, we might see this. If we were to say use 10 different categories, and instead of these phrases being like 4 words, they were like 50 words, then when we're trying to capture a embedding for the entire sentence, we're averaging together like 50 individual word vectors, and the actual meanings of all these individual words might get kind of lost in that averaging process. So sometimes they're not quite as precise as maybe using bag of words in that case, because things get kind of mixed together. Another drawback of the standard word embeddings is this is a little bit different than the context that we're worrying about. But imagine we're trying to get some sort of meaning for the word check. So I went to the bank and wrote a check. So that's the check in this case is gonna have a specific meaning. But if I also had another word embedding, another sentence that was let me check that out. Check and let me check that out is very different than writing a check, but the word vector is going to be the same for both of those. So you do get, for words that have multiple meanings, you do get a little bit of messiness because both their meanings are kind of are captured in the training process, and ultimately part of those meanings are probably lost. So word vectors are very cool, pretty powerful, but they don't solve everything, and ultimately left a lot of room for improvement that it was ultimately a lot has been developed recently, as I kind of mentioned at the start of this tutorial. All right, in this next section of the tutorial, we're going to kind of do a rapid fire overview of a bunch of different NLP techniques that are good to add into your NLP toolkit. And so the first technique we're going to look at is using regexes. So regexes are pattern matching of strings, and they're not a Python specific concept, but we can definitely effectively utilize them in Python. So real quick, I'm going to start with a quick overview of regexes. Basically, the way you can think about them is you could have all sorts of different types of phone numbers. So like 123, 123, 1234 would be a valid number. You know, maybe a different set of numbers that's the same format. 555, 555, 5555 would also be another valid phone number. Maybe you want to write it a little bit differently, and maybe you do like +1 dash parentheses 123 dash 123 dash 1234. These are 3 different ways to write a phone number, but they're all like technically valid ways to go about it. So one way we could use regexes is pattern matching on like figuring out if something's a telephone number or not. And so like in this case, one thing we could see is that it has 3 digits followed by some sort of punctuation, or maybe no punctuation, followed by 3 more digits, followed by 4 digits. And basically we could define a regex for that. And similarly for this like last one, you could define in your regex that it could have a +1 or plus some number optionally. And so regexes allow us to easily capture these different types of patterns and effectively add this into kind of like code that we're writing. So, you know, phone numbers, writing regexes for phone numbers is one thing. You also might have like a password checker where if you're like logging onto a site and they say, oh, you need 1 symbol, 1 character, 1 uppercase character, and a number in your password, and it has to be plus 10 digits or more. A regex can help the people implementing that site on the back end make sure that your password meets those specs. Email formats is another thing. So I think the easiest way to get into regexes is to just start right away with an example. So I'm going to say as the example is that say we want to match a string that starts with the letters A and B and they can have in the middle of the string, it can have any number of characters. It doesn't matter how many characters it has, as long as there's no white space. So we don't want any white space in what we're trying to match. And then it needs to end with the letters CD. So whenever I'm going about working on a regex, I usually will start looking at a regex cheat sheet to just remind myself of what we can do with regex. So I'll link this in the GitHub page for this tutorial. But a page like this has all sorts of useful tidbits. So ultimately what we're going to want to do is have exactly A or B, or exactly AB, which is going to be a group, followed by any number of characters. So if you see that there's this special dot or period, that's any character except new line. So maybe we will utilize that. And then there's these quantifiers. So if we can have 0 or more, 1 or more, 0 or 1, we can use these quantifiers. And there's some other stuff too, like word boundaries is useful. But let's try to write a regex for the case I just said. So I'm going to the site regex101.com, and it actually has the flavor you can test. So I clicked on Python. So what I said is it needs to be AB to start, followed by any number of characters, which is period, and then it doesn't matter how many there are. So it can be the star, that means it can be 0 or more, followed by CD. So that's like the basic implementation. As we can see, if I do AB, EE, CD, it matches. If I do BA, all of this and followed by X or something, it's not going to match that one because it doesn't start with AB and it doesn't end with CD. Continuing on, I said that there couldn't be any white space, so let's see if AB space CD works, and that does work. So now we need to fix our regex to disallow white spaces. Going back to our cheat sheet, we see that there's this not character, not A, B, or C. So we can utilize that along with white space, this character class. So we can do /s to do the white space. So we're going to do in this brackets, we'll do not white space. So let's go back to here. So instead of dot star, we're going to do brackets, not /s, close bracket, and then one or more of that. And so now we see that this works, but this one now doesn't because it has white space in the middle. If I remove that white space, it's now a match. That's pretty cool. One thing to note here is I could do something like XX, ABCD, XX, and that's still saying it's a match, or at least like it's saying the line is a match because that's included. If we wanted to make sure that it's exclusively this to start the line and this to end the line, we can use a couple more special characters. So this is the end of a string, and this is the start of a string. This is used without the brackets, and it means start of string, but if it's used in here, it means not. So we can add that. So start of string, followed by end of string. So now this one doesn't match at all. And that's the solution to that little exercise. So what does this look like in code? Well, we can quickly go to our Google Colab file. We can import the regular expression library, which is just RE in Python. And we can start out with our regular expression, which we can define to be whatever we want. So if we were defining the one I just described, it would be caret AB followed by not white space star, and then followed by CD followed by the end of line. So now we compile that to allow Python to know that that's a actual regular expression. And oftentimes when we're defining regular expressions in Python, we use a R in front of it just to help us highlight and help us know. And then we want to do, if we want to see if something has that, we could say here are like test or our phrases. ABCD, XXX, AB, XXX, CD, AB space CD. So only the first and third should match. So if we wanted to check if something matches, we can do for phrase in phrases. And there's going to be two main functions that we're going to use when we're checking for matches. We're going to do a regular expression.match. We're going to pass in first our regular expression, and then we're going to pass in the phrase that we want to see if it matches. And if it does match, I'm going to make this a conditional thing. So if the regular expression matches, then I'm going to have it append to a list called matches the phrase. So we'll have to find the matches list. Okay, and then finally, print matches. Run. Okay, so as you see, as we expected, the first and the third match. Now here's something interesting. Let's say we took away the requirement of this having to be the first and last thing in the line. And now we added something like AAA in front and then CCC. If we wanted to just check if a regex is in an entire string, so here we do have it in the string, but it's not the start. It's not the entire thing. There's places in this that don't match. If we rerun this code, you'll see that this regular expression.match function no longer says true on this one right here. So the other main thing we're probably going to want to use when we're searching text for regular expressions is re.search. And as you can see now, it still matches those two. And quickly, just to kind of apply this to the toy example that we've been doing, imagine we wanted to create a regular expression that matches read, story, and book. Maybe we're making some sort of hard-coded rule to find if something's in the books category. So I liked that story. I like that book. This hat is nice. As you can see, this regular expression, this is the or sign. It counts those. One quick nuance, if we wanted to make our regex more complicated, is that I could try to trick this and say like history, like instead of read, I could maybe say the car treaded up the hill. I don't know if that makes sense, but you can see that read is inside of that, but it is not actually referencing the word read. We'll notice that it's still matching those things. So one thing that's useful to know about is this word boundaries character within the regex. So /B means it needs to be between word boundaries. And now watch what happens when I run this again. No matches. So it now knows that story has to be by itself. And one thing that's nice too with that /B format is that you can have a period or something at the end. It knows that that's a word boundary. So that's like one way we maybe would apply it to our example that we've been working on. But there's so many use cases for regexes. All right, next we're going to quickly look at stemming and lemmatization in Python. And these are two techniques to normalize text. And what I mean by that is that in our first example with bag of words, we saw an example or a problem where when we trained the model with the word book, it didn't know the words books, even though to us, that's very straightforward. So one example of what stemming and lemmatization can do is take books and kind of reduce it down to a more canonical form of book. And it can do like several different things. So imagine these techniques could help you turn reading to read, books to book, stories. And now here's where there's a little bit of a difference. Stemming follows an algorithm and is not guaranteed to give you a actual physical true English word. So it might reduce it down to story. Whereas for lemmatizing, it would take stories, and it actually is using a dictionary, making sure that everything it outputs is an actual word. So that would output story there. So how do we use this in Python? Well, I think the library that's easiest to use... what did I do? The library that's easiest to access stemming and lemmatization is probably the NLTK library. So we'll use the NLTK library. Okay, so first off, we're going to need to import NLTK. And that NLTK stands for Natural Language Toolkit. Oh no, I'm trying to do too much. Import NLTK. And what we're also going to need to do is import a couple or download a couple of things for NLTK, and this should work out of the box, I believe. If you just do NLT, you get download. So we're getting stop words, WordNet, and I think the stop words is going to be for my next example. I don't know if we'll need that for the stemming and lemmatization section. All right, downloading all that. And now let's go ahead and start with a stemmer. So to get a stemmer, I recommend importing two different things. I recommend importing the tokenize library, which basically can take a sentence and break it into its individual words. As well as the actual stemmer. And we're going to use the Porter stemmer for this example. So I'm going to do nltk.stem. We'll import the Porter stemmer. And now let's go ahead and initialize that stemmer. And now we can just type in like a test phrase. So reading the books, we'll say. And to first we'll need to tokenize that, because if we just try to stem, if I just try to do stemmer.stem, this is all you have to do to stem of the phrase. It doesn't know how to process this because this algorithm expects a single word. So we're going to have to tokenize it. So we can just say words equal word tokenize of our phrase. And now we can just do stemmed words. We're going to do this in a for loop. So that for word in words, we're going to stem the word, stemmer.stem of the word, and we're going to append that to our stemmed words. Okay, and now we can do a join by spaces of the stemmed words as the final thing. So we started with reading the books, and the stemmer now got us down to reading the book. And this immediately can be seen to be very helpful for like that bag of words model that we built earlier, where if you didn't have many training examples, if you did stem the training examples you did have and stemmed any incoming phrase that you hadn't been trained on, it would probably help improve accuracy there. A couple examples to see. So if I said stories was one that was a little bit weird. See how it stems it to story. So it's not guaranteed to have a word, and sometimes you'll get collisions on two words that aren't necessarily similar. So there are some drawbacks, but it's a nice little quick trick to have. And I think I just want to check something with that whole tokenization. One thing to note is that you also might want to like strip out your punctuation or handle that a little bit separately if you're trying to return a phrase that makes sense, because as you can see right there, it at least the way I define this, you have to be a little bit tricky, because when you tokenize this, if I print out the words, it treats the punctuation as its own word. All right, moving on to lemmatization. Let's now from nltk.stem import the WordNet lemmatizer. So this is using this corpus called WordNet to help reduce these words to a more simple form. All right. So pretty similar to the last one, we could just do lematizer equals wordnet lematizer. And same thing for the example as before. We need to tokenize whatever phrase we use. Oh my god, I didn't mean to copy the cell. No. Delete this. I just wanted to copy this part. All right, so reading the books. Let's see what happens if we, I'll copy this too. No, not the cell, just the piece. And this will be lemmatized words. And it's pretty straightforward. Instead of stem, it's lemmatize. That's 2 M's. The word. And let's see what happens here. Print lemmatized, or I guess we'll join them again. Dot join of lemmatized words. All right, run that. What's gonna happen? Reading the book. Okay, It's a little bit different than our above example that turned it into read the book. And here's one thing that's a little bit trickier about using the lemmatizer with NLTK is it expects, for each of these words, it expects the part of speech. And by default, it says that each token is a noun by default. So that's why it converted books to book, but not reading to read. If I instead said these were all verbs, we'll see that it is read the book. I guess that's interesting. It still made books book. Is it books? He book. Yeah, I guess like if you think of books as a verb, he books it. That would be book. That makes sense. So I guess there is a verb, books. But yeah, the one caveat is if you're trying to effectively utilize this sometimes, you have to do some sort of part of speech tagging, which I believe I'll get to in the tutorial. And then maybe utilize that part of speech tag here to like truly reduce down all the words. But it might be also helpful to just reduce down all your noun phrases or all your verbs. So that is lemmatizing, and we'll move on from there. Next, while we're still looking at NLTK, we're going to quickly go over stop words. And basically stop words are the set of English words that are kind of most common. And sometimes we might want to strip those out of our phrases because they don't add much meaning to our sentences. So a couple examples of stop words might be this, that, he, it, the, these, them, those types of things. So we can easily do this in NLTK. So here we go. Okay, so we're going to continue using NLTK. We've already imported it at this point, and we're going to do, actually maybe it'll just it'll be helpful is if I copy in this just in case people run these independently. Paste in that, and then we're also going to have to copy in the actual stop words. So we're going to import stop words. And here we go. So our stop words are going to be I don't want to do stop words because otherwise I'll overwrite this import of stop words. So I'll just say stop words equals stop words dot words, and then we have to pass in that we want English, I believe. Actually, maybe it would work without doing English. So let's print out stop words. I think it's, oh, I guess you do have to specify English because I don't know what that means. Cool. I, me, my, myself, we, and I'm curious how many of these are there. So length of stop words, 179. So there's 179 words we might want to extract out, and this just gives us a nice easy interface to do it. So what we could do is we could have a phrase just like before. So here is an example sentence, removing stop words. I'll just say demonstrating the removal of stop words. So that's the phrase to begin with, and now we will tokenize that just like that we did before. So our words will equal word tokenize of the phrase, and then for word in words, well, I guess our stripped phrase, I'll call it that, equals, so if word not in stop words, then we can append it to the stripped phrase. You probably could do this in a list comprehension too, so whatever you prefer. Word, and then we can do dot join of the words, or we could just keep this as a list because I guess it might not fully make sense as a stripped phrase. We'll join them anyway. Join stripped phrase. Okay, here example sentence demonstrating removal stop words. So is, and, the, of were all removed as stop words. And how this could help us is going back to the word vector model from above. If we maybe said something like, I went to the bank and wrote a check, you know, we might get bogged down by some of these stop words in the actual meaning of this as we average together those word vectors. So removing the stop words might give us a little bit more precise capturing of meaning in something like this. That's just one example. There's other examples where removing stop words is helpful. Next, we're going to do kind of a rapid fire round of the rapid fire round, and I'm going to just quickly go through another library called TextBlob that allows you to access all sorts of different nice little things with language quickly. And it builds off the NLTK library, and it provides like a really nice interface for doing a lot of different things. So I'm going to just say various other techniques, and we'll look at spell correction, sentiment, and let's say part of speech tagging. All right, so when you're wanting to use this TextBlob library, I recommend actually just looking at the reference, and I will make sure I link this in that resources.txt I mentioned would be on my GitHub. It's a very straightforward one-pager that has all sorts of nice things that you can do. So from TextBlob, import TextBlob. That'll be our first line. As you can see, you literally just take in a phrase, and right here, b.tags, we've already done part of speech tagging. You can do like .noun phrases, .words, .sentiment. Do all of this stuff with like one line, like just a single dot something. So the first one I wanted to look at was the spell correct. And where is that? Correct. Here we go. So let's go to the code from TextBlob. Oh, shoot. From TextBlob, import TextBlob. Cool. Okay, so whenever we do anything with TextBlob, what we're going to want to start with is just basically making our phrase a TextBlob object. So we're going to go phrase, we can say whatever it is, equals, this is an example. And then what we're going to want to do is just do, we could even just surround this, or I'll just say TB phrase, so TextBlob phrase, so we're converting it as TextBlob and then phrase. Okay, and now with TB phrase, we already can do all sorts of nice things. So the first thing I mentioned was spell correct. So TB phrase dot correct is all you have to do to spell correct that. This is an example. What if I said this is an example and use two E's? see it's still, this is an example. If I use like 2 I's here, it probably will still think, look at that, it's correcting this very quickly. And when I mentioned that original goal of this tutorial was, taking tweets and processing it, you can imagine that a lot of tweets are misspelled and have this. So being able to, we could easily make this 2 lines of code, actually even a single line of code if we really wanted to get fancy. Do spell correcting on a phrase. That's pretty helpful. So what else can we do with text blob? Well, I mentioned you could do part of speech tagging. So I'm going to go back to our reading examples. So I read the book. So obviously we don't have any spelling errors there, but one thing we could do is get the parts of speech, and I just have to do .tags to do that. Okay, what do we say? Looks like you're missing some required data for this feature. Okay, so I'm going to real quick add this to my Google Colab file. And just like I downloaded some stuff earlier, I will run this. Cool, it's done. And now we should be able to do part of speech tagging. List object is not callable. It might have been just .tags. It might already be baked in. Look at that. So we have I, which is a noun. We have read, which is the verb. We have the, which is whatever DT stands for, and then a book, which is another noun. If you just look up like part of speech tagging, you probably will find information on the different variants. And so this, I'll link this in my GitHub. I found this page as a helpful resource to learn about the different things that you see. So we did see, okay, like DT is the, what do these things actually mean? Adverb, like we can just kind of look through this and help us find. So this is a terminer, the DT, noun is a singular, noun s is plural. So yeah, this has all sorts of useful information right here. So I'll link this to if you want to know more about the tags here. Another cool thing is we can do .sentiment. We might have to do sentiment like this. Let's see, go back to the reference. Yeah, it's just .sentiment. Okay. So the book was great. Polarity 0.8. So high numbers here are going to mean positive, but if I say the book sucked, it was so bad, right there, we see that has a negative sentiment because this is negative value here in the polarity. The book is another example. The book was horrible. Another negative example here. So you can look into the details of the sentiment to see that. But yeah, in this API reference for text blob, there's all sorts of really accessible, easy things you can do. So it's another great resource to utilize. And I just want to make the point of one of the main goals of this tutorial is to show you all these different things you can use so you can kind of build upon this knowledge and apply it as you see fit in your own tasks that you are working on. All right, so moving towards the kind of state-of-the-art models in natural language processing, I wanted to start with recurrent neural networks. So if you remember back to word vectors, one of the issues that we had with them was that they were kind of set in stone. And once you've trained your word vectors, no matter what way you utilize a word inside of a bigger phrase, that word vector that you've trained is the same. So we don't have kind of context-dependent word vectors when we're just using a pre-trained set of word vectors out of the box. So immediately, recurrent neural networks can help us kind of solve that problem. So here I have a diagram of a recurrent neural network. And so basically how a recurrent neural network would work with language is we would feed in words into the network one at a time. So we would have something like, the word check come into our network. And so that would come in, the network would process it and produce a hidden state based off of it, and also feed that hidden state to the next, layer of the recurrent neural network. So maybe the next word is out. And so that now we have check and out all feeding into the same network. Basically, we can do this as much as we want. We're always feeding the output from the last input back into the network. So we have check out the book. So basically, we're feeding this in and creating some sort of, at the end of book, we'll get some sort of final hidden state, and we can use this hidden state in NLP applications. And so what's nice about this is if we had another phrase that was write me a check, well, the way that check was used here is at the start of the sentence, there's no other words around it, and you're going to get a different kind of embedding for this check than you will when it says write me a check. Based on the context of write me a, the embedding, this final hidden state may be more related to banking versus check out the book would be kind of a more related to a hidden state that more represents check as in check it out. So that's like a little toy example, but that's ultimately like one of our goals with something like a recurrent neural network. But the recurrent neural network, for a while, this was kind of the go-to to build all sorts of state-of-the-art language models. But it did have some drawbacks, which ultimately got replaced by like the OpenAI GPT-2 model I introduced at the start of the video and some other types of models. So what are those drawbacks? Well, the first one I would say is that the long dependencies don't always work well with a recurrent neural network. So imagine you have the sentence like, I need to go to the bank today so that I can make a deposit. I hope it's not closed. While we are feeding in, we would be feeding in each of these words to the network. And like always that hidden state would have had some influence from each of these words. By the time we get to closed, a word like bank is pretty far away. So in the final output embedding, that hidden state, it might not be clear to the network that the thing that we're talking about that is closed is the bank because it's so far away in this sentence. So that's one drawback with recurrent neural networks. Another drawback is more on the performance side of things, is that because we're feeding these one token at a time, the sequential nature of that makes it tough to parallelize the training and utilization of RNNs and language models sometimes. And, we can't as effectively utilize modern GPUs. All right, so that leads us into attention. And a big paper that came out was called Attention is All You Need. And this kind of set off a whole new wave in natural language processing. So what is the difference with attention? Well, basically you can feed in a phrase, and as you iterate through the tokens in that phrase, and you can basically figure out what needs to be attended to. So if you like walk through this sentence, I need to go to the bank and write a check. Well, write, when we get to the word check, let's say, we're feeding these all in, and this is all being fed in at the same time using these positional encoding, so it doesn't have to be one after the other. But basically, if you get to a word like check, well, it will probably spike off write and bank as like relevant items to check. I need to go. Go might like set off, if you're looking ahead, bank might be triggered as like an important indicator to go, etc. So basically, we're based on what word we're looking at, our network kind of learns to attend to other words and figure out what's most important given a certain token that we're looking at. And to kind of bring that to a high level, the network we can kind of think of learns to ask questions about phrases it sees. And these are not, they're not actually asking, human questions, but baked into these attention networks. They're basically looking at each token, asking all sorts of questions on that token, and learning based on that token what else is important in the phrase. And this is a super powerful technique. And also this attention can work at a longer range of dependencies than in a traditional RNN. So this set off all sorts of really impressive stuff in the NLP world. So at the start of the video, I mentioned the OpenAI GPT-2 architecture. One thing to note about that is its forward nature. So basically the task that this is trained on is language modeling. So given some words, what are the words that are coming after it? And that's why it was really good at being able to autocomplete like a story. And when I typed in a phrase, it could utilize the fact that it's been trained on figuring out, on predicting what the next word should be based on what it's already seen. So that's OpenAI GPT. Then there's this Elmo network that's also listed here. I just wanted to note this one. I don't know as much about Elmo network, but one thing to note is that it uses LSTMs, and it's kind of the core of it. And an LSTM is a type of recurrent neural network. It's supposed to handle longer dependencies a bit better, but still compared to attention, I wrote the header as this as transformer architectures, but Elmo's not technically a transformer architecture. It's just another powerful language model. And then finally, what we're going to focus on right now is BERT, which is a bidirectional transformer architecture. And as a result of it being bidirectional, it really captures a lot of very impressive things about language that even like the OpenAI GPT model can't. So we're going to just look at how we can use Python to interact with the BERT model real quick. Okay, so to do this, we're going to use Spacey again. So I'll link this article on my GitHub page, but basically Spacey provides us with a really easy way to interact with transformers. And if you just follow this link, basically it gives you all the lines you need very quickly to get up and running. So let's utilize Spacey real quick. So the first two things we're going to need to do is pip install Spacey transformers and python-m Spacey download this model. Okay. So I want to make a title, not an italicized title. Transformer architectures, I'll say. All right, so we wanted to download this large model, and we also wanted to do a pip install of Spacey transformers. And what these exclamation points mean, I'm pretty sure, is that this cell should only be run once within Google Colab, so we don't accidentally download the model again. Okay, downloaded, and took a little while, but ran successfully. Cool. All right, and now how do we actually, now that we have it downloaded, we can go back to that article and see how we can actually use it. It looks pretty straightforward. And you can, if you're using a GPU, you could utilize these lines of code, and you'll note some details about that. But I'm going to I'll copy this in real quick. I think all I need is going to be, I'm not going to use this right now. I'm not going to use my GPU. Don't think we need NumPy right now. So I think you need to import Spacey and Torch, and it should be good. And then we're loading this large BERT model. And one thing to note about when we're using transformers, we're not going to train it. When we're using like BERT model, we're not going to probably train it from scratch. The BERT model itself is super, super massive. It takes multiple days on like some of the most powerful tensor processing unit machines to train this model, so it's not something you're gonna want to do, you know, at home. But luckily, they open source these models, and we can utilize them effectively. And one thing to note too is that even if you are loading in this model that's already been pre-trained, one of the nice features about models like this is that they can be fine-tuned, so you can fine-tune them on your specific task, and you can get some really impressive results by doing that. And that's a lot easier of a step than retraining it from scratch. Okay, so run this, see if it loads properly. If you're using Google Colab, you probably have to restart the runtime. Sometimes it doesn't realize where this model is unless you do that. Okay, cool. We have it. And now it's just like it is, like if we're using Spacey, now that we've loaded in this BERT model as our NLP engine, basically we can do the exact same stuff as we did for the word vectors when we were in that section of the tutorial. So here we go. So basically what I think I'm going to do is just define another set of training utterances and test utterances, just like we did here. I'm actually going to copy this in real quick because I don't think it's necessary to write it, because I want to change the example up a little bit. All right. So we're about to see the power of BERT and transformers in general. Okay, so this time I'm defining another category class, but this time instead of the difference between books and clothing, our two categories are book-related items and banking-related items. So here we've defined 7 different utterances, each with their associated category. And we can read through these real quick. Okay, cool. So let's build our model around this. And this is the exact same code basically that we used before. We just need to now all it changes is that we have this model as our NLP engine as opposed to the word vectors that we were using earlier. Okay, so I'm just copying in some code here. This is, yeah, as I said before, this is the exact same code as we were using before. So we can train it on the train X here. So I'm going to run this cell real quick. So we want to train our model on that, and we can predict new utterances here. So I'm going to just, to start as a toy example, say book. Okay, and as a result, it says books here. That's what we expect. One thing I want to note here, though, is one of our training utterances is check out the book. And so with that example I was kind of walking through is you could say check out the book, but if maybe you're writing about more banking related terms, you might say I need to write a check. So I'm going to just type in, you know, I need to write a check. And, you know, in our training utterances here, check, the word check only appears in the books category of our training utterances. And these 3 back here that are about banking, need to make a deposit to the bank, balance inquiry savings, save money, there's no mention of the word check. So a true test of the power of this BERT model is that, oh, does it know that when we say I need to write a check, we're talking about banking and not talking about this word we've already seen in the other category. And let's moment of truth. And look at that, I need to write a check. Utilizing the power of the BERT model and just like some small number of training examples, we see that it's banking related, which is crazy. And maybe you said, check this story out. Once again, it knows that check in this context is about books. So it's really impressive, the capabilities, because we've trained such a big model. Leveraging it is really, really powerful stuff. And you can continue playing with this. One thing I recommend looking into, as I kind of alluded to, is one of the nice things that you can do with a pre-trained model like BERT here is you can fine-tune it to a specific task. So here's some code that they use in Spacey to show you how you would fine-tune this NLP model to a specific, maybe classification task. So that's really useful. The next thing I want to mention is this interface that Spacey provides to BERT is really nice, but there definitely is room that if you wanted to build off of a model like BERT, you can't really do that. So if you wanted to dive deeper into these types of models, I recommend checking out Hugging Face's Transformers GitHub repo. And in that, they have pretty much all of the most popular different models that have come out recently within natural language processing. They have those models written in PyTorch that you can look around with. So like BERT here, this modeling BERT file, you'll see that pretty much an entire PyTorch model is defined here. So if you wanted to build off of BERT and fine tune it specifically or something, you could use this Hugging Face library. All right, so that's what we're going to talk about for transformers and how the code would look to easily interface with that. And one thing I want to note is that I can only teach you so much about the actual inner workings of BERT in this tutorial. I was kind of more focusing on quickly getting up to speed and using this in Python. But I will list out on the GitHub repo resources that you can go to learn more about these types of things that I've found useful myself. All right, that concludes most of what we're actually going to do in the tutorial, but I will leave this tutorial with an exercise that you guys can kind of tie everything together and really try to build your, keep building on your NLP skills. So if you go to my GitHub page, github.com/KeithGalli/PyCon2020, basically, I've curated some data for a NLP exercise you can work on. And the data, it comes from Amazon reviews in several different categories. And there's also a test set of Amazon data in several different categories, each the same categories. And the goal of this task is to basically use this training data and build the best classifier you can to properly categorize the reviews here in the test set. The kind of bigger picture context you could think about this problem in is, imagine you are in charge of the social media analytics for a large retail store, and you're getting people tweeting at you all the time about all your different products, and you wanted to build a model to automatically route those tweets to the appropriate parties that could handle questions about them. Then a model like this would be super useful. So there's the training and test data for that task. And I also provided this NLP exercise notebook. And in this, I kind of quickly walk through getting up and using this data loading it in as training data, loading it in as test data, building a model on the training data, which by default, the simplest model that I included here is a bag of words model, but I'm going to be kind of adding, by the time you probably see this video, I'll have several models included in here, but this bag of word model can help you get started on using this data. And then basically, based on that model, evaluate the performance on how you do on the test set. So as you can see, out of the box, bag of words categorized 65% of the test reviews correctly into their category. And if you wanted to break that down a little bit more closely, I calculated the F1 scores here for each category. And as you can see, like, it did a really bad job on the automotive questions, but did well on beauty and books. And you can kind of utilize this data as you see fit and play around with building different types of categorizers, classification models around this. A couple of recommendations I have. I think it would be really interesting to see how well a fine-tuned BERT model would do on this task. I also think it would be very interesting to take the bag of words model, but also leverage some of those other techniques we mentioned. So like lemmatizing words, stripping away stop words, maybe doing some part of speech tagging, see if you can leverage that into make it more important. All really interesting techniques to try to build more powerful models. What else do I want to say here? I guess quickly, I didn't actually show you what the data looked like, but if I actually clicked on one of these files, maybe something like beauty would be easier to see. I'll also link my source where I scraped all this data. Someone already did a lot of the grunt work for me, and I want to give them credit, so I'll have that included in the README of my GitHub page. But yeah, basically you have this review text always talking about the category here. So this is beauty, so like outstanding top organic shampoo. What our model we would expect to learn is off of shampoo. One thing to note here is this is not perfect data. You'll get some reviews that are just like really good and thanks, and they don't give us much information, so we're never going to be able to get like 100% on this task. But maybe another exercise you could work on is how could we strip out these kind of non-specific types of words and not use them as training information and test information. All right, we're going to end this tutorial here. Hopefully you had some fun learning about some different NLP techniques in Python. There's a lot we covered in this video, and hopefully my goal out of this tutorial was for you to all see some of these techniques and have them in your mind so that you could take them and kind of build on your knowledge and apply them in different areas. So really it's like seeing all of what you can do and then taking it from there and going. Also, just a reminder before I leave, if you have any questions or anything, feel free to connect with me on LinkedIn, Instagram, Twitter, and you can search up Keith Galli, one word, you'll probably find me. And also, if you want to find more tutorials that I've posted, you can check out my YouTube channel, youtube.com/kgmit. Thank you very much, PyCon, for having me. This was fun, even if it wasn't in person. It wasn't what I expected, but it was exciting to go through this process, and hopefully we'll be there in person next year. All right, take care, everyone. Thanks for watching. Peace out.